right into the next panel now. Now, this panel is discussing the role astronomy should play in public outreach, and this includes the challenges and opportunities seen by the astronomy community today. For this panel, moderating, we have Hussein Jerda, and he is the head of communications and public outreach at the Space Telescope Science Institute, and he will be moderating this panel. And then we have Dr. Judith Pfeiffer, who is a professor of astronomy at the University of Rochester, followed by Dr. Neil Brandt, who is a professor of astronomy and astrophysics at Penn State. And finally, we have Dr. Martin Elvis, who is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Now I'll hand it over to Mr. Jerda.
Welcome to this session. It's a very exciting session. We have three terrific speakers, and I will be moderating. And our format will be that we'll have about 10-15 minutes talk for each one of the moderators, followed by question and answer period. This is a good topic for people like you who are starting their careers in the space sciences and technologies. It's an exciting time, and the world is changing. There are tremendous opportunities, and like the previous speaker said, I wish I was in your shoes. Our first speaker is Judy Pfeiffer.
I guess it's on, is it? Are they going to turn down the lights for us a little bit? Yeah? I think all of the speakers want the lights down slightly so you can see them. Yeah. Hi, I'm a member of what one of the previous speakers called the silent gen. That is, people over 70 who are barely involved, they think. But because I'm the oldest of the panelists, and I knew that two of the other panelists were planning on speaking of fairly specific topics, I decided to focus my remarks on a sort of broad brush approach to astronomy in the future. And the picture that we see up here, it's a little hard, unfortunately, to see, but it's a composite illustrating the different, with each color representing a different wavelength range of telescopes that are observing or have observed in the past. The X-ray and ultraviolet is the sort of purple-blue color, and the visible Hubble is a yellowish color, and the red is the infrared. They all represent, of course, different components of the galaxy that we're looking at, a spiral galaxy like our own. The infrared primarily outlines the dust lanes in the spiral arms. The visible shows mainly the older population of stars. The X-ray shows and the ultraviolet show quite young, hot young stars and hot gas. Okay, I have posed a number of questions for your generation. The first thing I want to do is congratulate you for early on assuming responsibility for the future of space astronomy. I was saying to one of the other panelists that when I was your age, it never occurred to me that I would be worrying about the future of space astronomy, and so I'm pretty impressed that all of you are here today doing just that. The questions I think you need to be considering for the future, and I'm assuming that most of your future will be tied up in astronomy anyway, science, the science side, with NASA or an equivalent agency, is the proper balance between the flagship science missions, the very expensive ones, versus the focused smaller missions. Then I wanted to say that it's terribly important that early technology development take place, and NASA or whoever is doing the funding has to, in fact, invest more in getting the technology right, and I'll explain some reasons why I think that is true. We have to, of course, talk about the role of private versus public funding for astronomy. This is an issue because while commercial applications play a big role in private funding, What role do they play in science funding, and what are the problems you have to be aware of when that happens? There is a fair amount of political influence on which topics are chosen in astronomy, which missions go forward, and I want to talk about that. I want to talk about the extent to which public outreach and educational benefit influence, if at all, the scientific directions. And finally, can we keep science from being politicized in some of these ways? We are accustomed to seeing beautiful images from the space telescopes. I showed you one that includes images superimposed from Hubble, Chandra, and Spitzer, the visible wave, X-ray, and infrared missions that are currently still up there and gathering observations. The way that NASA works is that every couple of years there's something called the NASA Senior Review. And what the Senior Review does is there's a collection of senior astronomers and physicists interested in astronomy who get together and decide which missions should have the highest priority and which should maybe be downsized and which should be turned off. And so this is a role that you're probably not thinking of training for, but it's something that you will have to assume one day as a future scientist. That is, trying to decide how the dollars get spent. Flagship missions are expensive. For example, the next one to come along is the James Webb Space Telescope, JWST. This is a telescope that will have a 6.5 meter mirror. It's an infrared mission. It will be be launched in either late 2018 or I think more likely at a later date. And the cost as of a year ago, last summer, had risen to $8.7 billion, which is a big hunk of change. And I would like us to consider certain things about how we could control costs for flagship missions. JWST will definitely be very, very valuable. I mean, there's no question about that. But meanwhile, no other missions except very small explorer missions are going to be moving forward to launch until JWST is launched. Hubble, which of course is still up there after 22 years of servicing, has exceeded 11 billion, and that does not include the cost of the servicing. I mean, we're talking about the marching army costs. So we have to talk about cost-saving measures so that they could be applied at the outset of a mission in order to enable a broader spectrum of missions for astronomy for you and your future. We can't see this because of very well because the lights are on, but I just wanted to show you some images that further talk about what we saw on the first slide. I'm interested in star formation, and this is the Orion region. And the one on the left includes Hubble data and Spitzer data. It's a composite image where you're looking at the ionized hydrogen and nitrogen gas that is in the Orion Nebula, and dust emission primarily from something called polycyclic aromatic hydrocarbons, little teeny soot particles in space from Spitzer. And on the right, the very same region is imaged, but this time Hubble images are combined with Chandra. And you can see if you look closely, pink and blue stars. They are mainly the very young stars that Chandra is identifying. Now, when we do public outreach in astronomy, we have a great vehicle. We can show these beautiful images. The public is not necessarily interested in the content that those images provide, nor the spectra that are an important part of it, nor astrometry or other things that come about. But nonetheless, because they provide the tax base, it is important that they be excited by the astronomical missions that cost so very much. The educational benefits are pretty profound too. At the K through 12 level of education, at the undergraduate level, I'm sure you've all been exposed through your lifetime to a lot of material from space experiments. And this is an important thing because it allows your perspective from an early age to be pushed forward. And I think that's an important benefit. Are there alternatives to these escalating costs of these flagship missions, such as Hubble, such as Spitzer, such as JWST? Well, small focused space missions are a very important component. And if they are given additional attention while still moving the flagship missions forward, we stand to benefit a great deal. I think that my colleagues on the panel will be discussing some future missions which may or may not be flagship and may be small focused missions. One thing that is unusual about astronomy is that at the outset of a mission, often the costs that are identified are a terrible underestimate. And it's not really fair to the public, to the Congress, to anybody to underestimate the costs so dramatically. Mission creep is something you've heard about probably. There's a lot of politicization of science, needs to be eliminated and downsized. Technology development, I'm going to give some specific examples of some of these things in a minute. It should be completed in advance of a large mission proposal. Obviously, you all know about Hubble and its mirror. End-to-end test before launch is an important thing. And private investment, we have to talk about how that can be used for science. Okay, let's talk about the honest appraisal of costs. JWST, when I first was hearing about it, was costed at $2.5 billion. At that time, Spitzer, the Spitzer Space Telescope, was costed at the same amount. Now, Spitzer was costed too high, but it was incredible to anybody who was listening to the initial estimates to think that you could possibly put into space a mirror that had to have elements that folded out, that had to be aligned coherently, that the focal plane was paved with pixels because of large format arrays, and that was being launched to a quite distant point. These things didn't make any sense. $2.5 billion wasn't reasonable even back then. Now Spitzer, on the other hand, had to be downsized and technologically reinvented. And it was a very hard period. I was involved with the Spitzer program, and so I remember how wrenching the decisions were. But it finally came out at $0.7 billion. So that's a much more rational cost. A lot of time and energy is invested in trying to be building or planning a large mission that is costed too high or too low. Both of these things have to be addressed. And as far as optimizing technology in advance, I don't know how many of you are aware that the James Webb Space Telescope has gone through now 2 periods of the detector arrays that are the heart of their cameras and spectrographs have had to go through major replan and redo twice now. And this is despite the fact there was a period when those very same detector arrays had been chosen, but the initial tests were wrong. They were incomplete. They just did not approach discussing all of the problems. This is partially on the shoulders of the industry that provides them. They weren't necessarily upfront all the time. But it also means that the tests that the astronomers, the engineers, the scientists should have done weren't done early enough. And so you had to go through a whole generation of providing these detector arrays, and then it's now being redone. It's not finished yet. It's going through that stage right now, and they look very good. I think it's going to be fine, but it's a big investment and cost. This causes, of course, delays. Delays mean marching armies have to be supported because you don't get rid of all of your competent people just because there's been a delay. And so those people have to be paid. And so this is really a big problem, and it's something that I hope your generation is practical enough to take hold of it and try and insert a fair amount of reason into the process. Management control to keep the projects from vastly underestimating costs, that's also needed. Here's an example of a small focused mission and technology investment. You heard Martin Elvis talk last session about going to asteroids and mining them, etc. Well, I'm working with a mission called NEOCAM, Near Earth Object Camera. We smartly have been given technology development money. We are only going to do 2 bands in the infrared. One is from 3 to 5 microns, that's the blue band, and one is from 6 to 10 microns, that's the red band, and that's to characterize the thermal emission from near-Earth objects or asteroids that are close to the Earth. There's roughly 7,000 of these things that are known. There's not one that has been identified yet that Martin will be able to take advantage of. And so one of the purposes of the NEOCAM mission is to, in fact, identify near-Earth objects, new ones. And how are they going to do that? Well, at 10 microns, you are at, oops, I don't know what I just did there. You are at the peak of the thermal emission at 10 microns of these asteroids. You can see that independent of their albedo, you can see them almost equally well. The very reflective ones, for example, this green one has a visible wave component that can be detected from the ground, and there are several asteroid surveys. But the dark ones, this is not hardly the darkest one. That has an albedo of 0.04, and there are many darker ones than that have been found. They can't be seen nearly as well or at all in the visible. There's a space, there's a discovery space that is available in the infrared that is not available in the visible. You can get excellent radii if you can combine visible and infrared data. Infrared data alone provide the radii of the asteroids, but not as precisely as if you had both wavebands available to you. And my group has been just recently, say since July, successful and finally, after about a 10-year effort, getting the 10 micron detector arrays to the point where they work well at a temperature of about 40 degrees Kelvin. That's important because you can passively cool focal planes to 40 degrees Kelvin. That is, you don't need to take cryocoolers or cryogens into space. You can exploit the cold temperatures of space to move forward. And so we are going to be working on this project. I was just going to show you the orbits for space missions. You can't really see it, so I'm not going to belabor it. It just shows where L1 is located and where L2 is located. Now, there's a competing group headed by a couple of ex-astronauts who want to do something similar to NEOCAM. They call it B612. And if you are a science fiction reader, you probably understand the reference. But in any event, they are soliciting funds from the public. They have a wonderful advertising campaign. They have press releases and so on. I believe what they're mainly interested in is finding asteroids for commercial exploitation. But they don't have experts or a lot of experts on their board who are experts in either number one, asteroids, or number two, infrared technology, which is sort of interesting. They work with Ball, and Ball has certainly infrared technologists there. But if they're going to use the data that they acquire for science, then they need to have responsible and knowledgeable team scientists. They need detector and instrument technology development, and they need peer reviews at various intervals. In NASA EAS, things called PDRs and CDRs, preliminary design reviews and critical design reviews, to make sure that everything is going to accomplish the science that was intended. So how are you going to balance this in the future? There's certainly a place for private enterprise, but it would be a wonderful thing if some sort of collaboration could be encouraged between the private financing and the public financing, so that the space, also, the astronomy, the science also gets handled properly. And I just wanted to point out that it's well known that various members of the House and the Senate back specific science missions. And this plays a role when it comes to time for appropriations. This is maybe not too healthy because it has less to do with the science and more to do with what is good for their particular political jurisdiction. Similarly, the public loves the Hubble Space Telescope, and it's a great mission. But should that influence science choices? It's not always the case. I could name an example, but will not, of a very much less capable mission that was pushed by the public and, of course, was launched. Future missions that are exciting and in the future. Am I running out of time? Yeah, okay, I've run out of time. The James Webb Space Telescope and WFIRST, those are the decadal surveys, top flagship missions, and your job is cut out for you. There are roles for scientists, technologists, instrumentalists, policymakers, politicians in determining the direction that space astronomy is going to take.
Thank you so much. Our next speaker is Professor Brandt.
Hi, so I'm going to take up the new opportunities theme of this panel discussion, and I'm going to talk in a focused way about new opportunities for discoveries about supermassive black holes. And I'll focus on the period of about the next decade, when you'll all be going off to graduate schools, maybe getting your first jobs and possibilities to do work in this area. So supermassive black holes most obviously manifest themselves as active galactic nuclei. This is where the supermassive black hole is accreting material from the central part of a galaxy and is thereby producing brilliant radiation that can vastly outshine all the stars in the galaxy in which it lives very substantially. And we want to investigate many aspects of these active galactic nuclei, ranging from the very small scale region where gas is swirling into the black hole, where you have extreme strong gravity present, where you have extreme temperatures and extreme velocities. On larger scales of sort of light weeks, we also know that these active galaxies, many of them expel material, very substantial amounts of material, as well as eating gas. They blow gas outward. And these winds are very important. We're trying to understand them, as well as the obscuration that they and other material in the central parts of galaxies cause. And then on the very largest scales, we've learned over about the past decade that the black holes have very strong interactions, very strong interrelations with galaxies, with groups of galaxies, and with clusters of galaxies. And so black holes are not just sort of pretty ornaments. They actually have a very important role in shaping how galaxies have formed. And so we've made huge amounts of progress in all of these areas. And the bottom line from my talk is going to be that we actually have tremendous opportunities over the next decade to make major advances in all of these areas. And there are real challenges as well. We've heard about some of those from some of the previous speakers. Martin's going to talk some more about those in the next talk, but I get to be the optimist today and to tell you all the exciting possibilities. And I think many of them will actually be realized over the next decade. And so my talk is going to aim to hit many of the highlights and again, focusing on things that I think are likely to be real. So as we've heard, the past decade has been wonderful for astrophysics in general. In X-ray astronomy, which is the area where I personally work, we've been extremely fortunate. We've had 6 to 7 X-ray missions, highly capable X-ray missions, studying supermassive black holes as well as many other cosmic objects over the past decade. Here's images of many of them. And X-ray astronomy, as well as astronomy more generally, has delivered incredible things in understanding black holes. Again, many of the things that I just told you about, probing the regions very close to supermassive black holes, understanding how many black holes there are over cosmic history, how has the black hole population changed over the history of the universe, huge advances there, as well as this whole idea that black holes are related to galaxies and clusters of galaxies and groups of galaxies. Now, those things have all made tremendous advances over the past decade, and I want to talk to you about how we can hope to advance those things. Now, the next decade, again, as we've heard from several of the previous speakers, is going to be a lot leaner, unfortunately. And it's easy to get worried with the seemingly endless bad news coming out. You look at any science magazine, every month or so, you will see at least one significant story, such as this one, where you hear about an astronomical deficit forcing the downsizing of U.S. telescope projects. And that is true. There are real hard fiscal realities, and it's going to be hard to keep up the same level of large new initiatives. But nevertheless, I personally think this next decade is going to be an incredibly exciting time for studying supermassive black holes, as well as astrophysics more generally, and that we should be able to make major progress on many of the remaining big questions that we're trying to answer about black holes. And there'll be more than enough to do. There's certainly going to be plenty of data, as I'll highlight shortly. However, we are going to need to adopt some different approaches to move forward. As we've heard, budgets are tight. This sort of large mission, launch many billion-dollar class missions, is just not going to be sustainable for at least the next decade. And so we're going to have to adopt different approaches, and I'm going to highlight some of those approaches. First thing to mention is that we are still blessed by having the investments of the past decade up there and still operating. Many of the missions that were built and designed over the past decade were wisely, I think, designed to have long lifespans. And so we can hope to keep operating at reasonably economical expense compared to what it costs to build them, many of the best missions that we currently have. Here, for example, is the Chandra X-ray Observatory. This has been a fantastic mission. It was launched in 1999. And it's been producing exciting science, I guess, over almost half of your lives now. And it will. And what I can tell you is it's still producing as exciting science today as it did in the first few years after launch. It's doing fantastic stuff in a broad range of areas. And Chandra is quite plausibly a 20-year mission. Here's a plot showing the sort of state of health of all of Chandra's major subsystems. Clearly, you're not going to be able to read that. The point is that the colors of the boxes indicate status, and there are no red alerts on Chandra right now. It's been going since 1999. It's operating very, very well for a mission that's that old, and it can be operating for considerably longer. Similarly, we can hope to have long lifespans from other missions: Hubble, Kepler, XMM, Newton, Swift, Fermi. Many of these missions can go a long time at quite reasonable expense. And now, to keep the science still exciting, we're going to have to adopt a different approach. We're going to have to take on very ambitious projects with many of these missions to keep the science from getting stale. And I think there's good opportunities for that. So that's one possibility for the future. Furthermore, there are a number of new missions coming along. I am going to just highlight 3 of them in the area I know best, fast X-ray astronomy, and where there are a number of very powerful, small to medium missions that only cost a few $100 million rather than billions of dollars, okay, that are very powerful, specifically being enabled by wisely utilizing focused technology. Okay, here are 3 of them. This is the New Star mission. This is a fantastic mission that just recently launched over this past summer. Okay, and I'm involved in the team. Martin's also involved in the team. It's giving fantastic data already. We're all very excited. This was a NASA small explorer mission, so it's a very economical enterprise, but it wisely utilized technology to push things forward. In particular, this one utilized this one obtained the first sensitive X-ray imaging at high X-ray energies, from 5 to 80 keV, energies that are similar to those that your doctor uses to look at your bones. this enables us to find very highly obscured active galaxies out in the distant universe that would otherwise be hard to find. That's one example of new technology, in this case, multi-layer coated mirrors, which enable the focusing of the high-energy X-rays. Here's another one. Astro-Age is a mission that should be launched in 2014. It's a combined Japanese-US mission. It's going to utilize microcalorimeter detectors, a new type of X-ray detector, to give you very high throughput and very high spectral resolution spectral data all at once on active galaxies to probe the regions very close to black holes. Another one, eRosita, this one's actually a German-Russian mission, is a survey-optimized X-ray observatory that will conduct a survey that's 30 times more sensitive than any that we've had previously over the entire sky. And this one, we expect to find about 3 million active galaxies, 3 million of these accreting supermassive black holes. And so those are some examples of how wisely designing, highly focused missions that utilize exciting technology in one direction or another can lead to great science without incredible cost. Now I'm going to just briefly talk about some multi-wavelength possibilities. Here's another facility that I hope many of you have heard of. It's the Atacama Large Millimeter Array. Have people heard of ALMA before? Okay, you should, because your taxes and taxes of all of your countrymen, it's been $1 billion expense to build this thing. Okay, and so we should definitely push hard to use this thing. This is an observatory located in northern Chile. It has 66 telescopes, they're 12 and 7 meter diameters, and it can do all sorts of exciting things. For black holes, one of the amazing things about the sub-millimeter observations is that as you take a source and you move it out to high redshift, normally its flux becomes fainter as you put it farther and farther away. But due to the way that the spectral shapes of galaxies and active galaxies work, as you take a source and move it out further and further away with ALMA, it actually stays at the same flux. The shifting of the spectrum compensates for the drop-off of the flux with distance, and the source stays bright out to very high redshift. So this is going to be an extremely powerful facility for studying active galaxies out in the very distant universe. We can get redshifts for them, we can measure spatially resolved star formation in them, we can get dynamical masses for them, so this is an extremely exciting thing in the distant universe. Nearby, you can also do a lot of exciting stuff. You'll be able to map out spatially the obscuring material that we know is commonly present in the centers of many of these active galaxies and understand it, not only spatially, but also via velocity maps. Then just to wrap up, the other thing I want to highlight is this relentless exponential advance of information technology. You all know about Moore's Law, you know about the growth of hard disk sizes and so on. This is something that always seems to get better, even in lean, tough times like the ones we're going through now. It always gets better. And we need to exploit this rapid growth for supermassive black hole studies. One way to do that is with large numerical simulations of accreting supermassive black holes. There are many very powerful supercomputer computations being done now to simulate how accretion flows work, to simulate how jets are launched and how winds are launched. And taking these simulations and combining them with the data that we already have will allow us to make tremendous new advances. Half of the time, honestly, the data that we have are already good enough. It's that we can't understand the data that we have and connect it to proper physics. These types of simulations are enabling that. And then to end, my other favorite thing are the deep, wide, and fast surveys that are being enabled by this type of information technology. These are missions such as the Large Synoptic Survey Telescope, Pan-STARRS, and the Palomar Transient Factory. These are, again, made feasible and economical by these information technology advances, and they are able to go out and survey enormous cosmic volumes by having very large fields of view and very sensitive observations. They can repeatedly survey enormous cosmic volumes to follow up millions of active galaxies, to find new transient objects. The Large Synoptic Survey Telescope, for example, every night will survey about 3,300 square degrees of sky. That's 8% of the sky, down to extremely sensitive levels. Here's a typical image you can hope to get from the LSST. Every night it will monitor 3 million accreting black holes. You can hope to discover 20 large AGN flares from jets and accretion distance abilities. We expect every 3 days or so you'll detect a star that flies in too close to a supermassive black hole and is torn apart by the black hole's gravity. You'll also hope to detect strong microlensing events, and if we're lucky, we can find things like binary supermassive black hole in spirals and mergers. So there's tremendous opportunities coming from information technology advances as well. So I'll just put up this summary of opportunities, and thank you very much.
Thanks, Neil. Our third speaker is Martin Elders, and he's from the Harvard Smithsonian Observatory.
Thank you. Okay, this is great. Neil has told you some of the motivation for why I want greater observatories in the future. And Judy's gone through a lot of the excitement about what you can do with small missions, and that in fact is the right tactical response, I think, in the short term. But in the longer term, you do have to have bigger mirrors because you can need to collect more photons in order to get a good enough signal to divide it up finally. And this is where astronomy hits the funding wall, which is what I'm talking about. It's not just astronomy, it's a natural tendency for all programs to grow and grow and exponentiate until they can't go any further and societies can't afford them, starting with the pyramids that got bigger and bigger until they had a bad effect on the Egyptian economy. The cathedrals would get bigger and bigger through the Middle Ages until people couldn't afford them to build any bigger ones. And to take a more recent example, the US superconducting supercollider, the accelerator that was going to be far more powerful than the CERN Large Hadron Collider that found the Higgs particle recently. We'd have found it years ago and gone beyond it, but the cost grew out of control, and Congress said, you want that much money for one experiment? No, right? And we've reached the same situation with space physics, space science right now. And as Judy nicely showed in her slides, that we have 3 great observatories now, Chandra in the center there, Hubble on the left, and Spitzer on the right. And the fact that when you look at the same object with the 3 different wavelength bands, you see very different things, yet they complement each other and produce a single coherent physics picture is wonderful. It leads to rapid advance in our science. The problem is that the era of these great observatories, which is not my name for them, but NASA's name, they were sold as a set, and correctly so, because they are complementary and synergistic. It's about to end, right? Those are old telescopes, and there's no particular reason why Chandra should fail any time now, but a prudent person would not bet on it lasting past 2020. We have to think about replacements. Well, NASA, of course, has been thinking about replacements, and the whole community have, and what we're building is the James Webb Space Telescope, which you heard about, a huge near-infrared and mid-infrared telescope that's built as a replacement for Hubble, which is great. It is awesomely powerful. The reason it's moved to the infrared is because the high redshift universe is there. That's where you go study the things that Hubble saw at lower redshift. So the early universe, back in the first giga year of its existence. But it cost $9 billion, and you may have heard it got close to being cancelled a year or so ago. If it has another cost overrun, another $1 billion or 2, then it's going to be looked at by Congress very closely in these even tougher times. And I really hope it's not cancelled, but it could suffer the same fate as the superconducting supercollider. The problem is our great observatories have now gotten too expensive. You can see why. The 3 space telescopes that we've gone through 3 generations, starting with IUE in the late 1970s, a half-meter sized telescope. There's a person in the bottom left for scale, if you want to see what's going on here. Through Hubble, which is the mirror that she's pointing to there, about the size, a bit bigger than a person, 2.5 meters tall, to the James Webb Space Telescope, the golden thing with the hexagons. You can see why things get a lot more expensive, because we need a lot more photons. And with the current technologies, that means a lot more money. The same thing happens in planetary exploration. Here's the Mars example. There are the 3 generations of Mars lander, a rover, and you can see how they've gotten bigger, as we heard in earlier talks, from the tiny Pathfinder through the Mini Cooper-sized Curiosity. And it's not just the size that got larger, but naturally the cost got larger, and there's an exponential rise. The 3 points on the left of those 3 rovers, the Mars sample return continues that exponential rise to at least $6 billion cost. So in the same territory as James Webb Space Telescope. And I don't know much about the Earth observing systems, but I'm told, I've got this out of the Physics Today article, they seem to be in a similar state of peril. Things have gotten too expensive and they can't afford what they wanted to fly. So we've hit this space science funding wall, right? And as Herbert Stein's law says, if something cannot go on forever, it will stop. And I don't want space science to stop. So the imperative is bring down the cost. And this is where anyone who was here at the previous talk I gave in the previous session will start to see something familiar. What is the cost of getting to space? Well, Apollo 11, 1969, $20,000 a kilo in today's dollars, right? 40 years later, shuttle cost, $20,000 a kilo. Nothing has changed in 40 years. No wonder things are still expensive. If computers had followed that path, we would be in trouble. We would not have cell phones, smartphones. So, the problem is that the cost to orbit doesn't dominate the mission cost. It's maybe 20% of the mission cost, but it drives the mission cost. And as engineering students, most of you, I think, will start to see why and appreciate why. Because every kilogram is precious, every 100 grams is precious, you have to go to extreme engineering practices to bring the mass down. And bringing the mass down is expensive. So imagine if you could get to 1/10 of the launch cost. Now, we scientists would say, oh great, we can launch a bigger mirror. But if you just push those guys back for a while and say, whoa, wait a minute, what would that do to change the space engineering practice? I think you'll see that it's a lot. It makes a revolutionary change in space practice, and I'm hoping I can get a study at Caltech, the KISS Institute, to look into the details of this. But just imagine, you no longer have to use the fanciest alloys, machine to the tightest tolerances to get the absolute minimum mass. You put in a little steel beam instead, right? Doesn't matter, it weighs 3 times as much, so what? Mass is not important anymore, not driving. Suppose you can afford to shield your electronics with heavy metal casings and run them at, and have big solar panels, so you have plenty of power, and you can run in a sealed environment at atmospheric pressure. You don't have to have custom-made rad-hard chips that have been tested out the wazoo. Instead, you fly off-the-shelf electronics, maybe avionics, but not at space levels of cost. And you can afford to get reliability through parallel redundant systems instead of optimizing the one chip to make sure it works perfectly, because you have the mass budget to do it. It will change your engineering practice. You get a virtuous cycle of decreasing mission cost. This is what I want to enable. Now, that's great, and there's a possibility that it will happen even if the Falcon 9 Heavy that Elon Musk has talked about delivers as promised, $100 million for 50 tons to Leo, then that cost of $20,000 a kilo comes down to about $4,000 or $5,000 a kilo, and we're entering the territory where this will be a possible approach. So I think this era could be about to start, even without what I'm going to say next, and this will be familiar to the people who are here. This is Elon Musk standing in front of a Falcon 9 rocket, and it costs $50 million. He charges $50 million to launch this. And to give an idea of the possible cost savings, does anyone know how much the fuel costs are for that launch?
About 200 grand?
Yeah, $250,000. So 0.5%. Now you're not going to get away from the fuel cost, but if you can get down anywhere near that by improved engineering or whatever, reusable systems, which he's working on, you'll know, then you can really have very sensible reason to believe that the launch costs will come down, and it will change space engineering practice. Now in the long term, as you all know, I'm pushing that capitalism is the way to bring down costs, because NASA and DOE and DOD, they don't care about bringing down costs fundamentally. They care about mission success, reliability. You want to keep your surveillance capabilities, etc. And you don't want to crash land on Mars. You want to land safely, so you have to be very careful about reliability. But when you are a capitalist, your job is to make money, and you will be out of business if you let costs run away, and that leads to my aphorism, greed is the counterweight to caution. This is what will bring costs down, right? Somebody has to be wanting to make money out of this, otherwise you will have endless rounds of tests and endless rounds of refining the design because of reducing the risk. The last few percent of risk, and this is what Chris Lewicki always talks about at Planetary Resources, the last few percent cost the most. So you get out of that by having redundancies. Space tourism is one way in which this will happen, because they're trying to make money and they will take sensible risks, not crazy risks. Who knows what will happen after the first accident? There will be a first accident. I hope it is a long way away. But it's a commercial enterprise, so long as we won't have Challenger-style inquiries about a government level. It'll just be a commercial problem. If we don't have that we have an inquiry every time a commercial jet flight goes down, but it's not stopping the industry. And it didn't even when they were much more common. But of course, I like platinum group metals, asteroid mining as a profitable path to the future. I think that's really going to be what we use in the longer term to get a long way from it. And then, when the costs have come down, we'll be able to afford really visionary type missions. This is a terrestrial planet finder interferometer, a set of very large James Webb scale mirrors acting as an interferometer, many hundreds of meters apart, and they will be able to image Earth-like planets which are now being discovered around distant stars, actually fairly nearby stars. But still, we will be able then to be able to point at a star in the sky and say, this star has an Earth around it, and here's a picture of it. There are great things we can do if the mission costs can come down and beat the funding wall. Thank you.
Thank you. We have time for a few questions. Any questions?
When the Hubble telescope is no longer in use, would they deorbit that or keep it up?
I believe the plan is to have a organized deorbit, so it doesn't hurt anyone. You would actually would
that is true. That is true.
Okay.
It costs a few $100 million. Having discovered that the people who work on Hubble, that's not true. They're actually planning on boosting it up into a permanent graveyard orbit. It's way above the other satellites, and leaving it there, it'll stay there for 10,000 years.
Oh, great.
It's worth that much if you didn't care about that, but you don't want to
Be a tourist destination.
Any other questions?
Very quiet.
Yeah, I've got a question.
Yeah.
How do public opinion has played a large role in Hubble being such a success? We get beautiful visible images back from that. How do we encourage the public that isn't the group in this room that James Webb has the same drive and the same need for support that Hubble had?
Well, I would guess that a successful mission will go a long way toward that, because you'll also be getting beautiful images from James Webb. The same outfit that runs the Hubble is also going to be dealing with James Webb, and you need a well-coordinated public relations arm. And so I don't doubt whatsoever that the support will be there, but it will have to be launched first. Anybody else?
Were you asking about after it's launched or leading up to the launch?
Both, really.
Well, I think the people who advocate for JWST have very effectively tied it to the Hubble Space Telescope and they can sort of adopt all the positive traits that Hubble gave. You know, until you have it in orbit, you can't show pretty pictures, but there are beautiful simulated images that are available, and those have been widely distributed. So those are the ideas that I think people have done. And do you have any other thoughts or suggestions yourself?
Yeah, I think making it the science case is a one way to go, and another way is to make the public aware of the value of the products that the Webb telescope will give. And Hubble has been tremendous. As you can see, it brought science to the world, the classrooms and the museums and libraries. You ask anywhere in the world what Hubble is, and they will tell you what it is, because the images are just amazing.
Also, NASA maintains a speakers bureau for missions, and there are some very good speakers associated with JWST that can be brought to whatever institution you are. For example, my institution, the University of Rochester, is having John Mather, come and speak to us in January. And he is a wonderful spokesperson for JWST. So different organizations should take advantage of that.
Yeah, he's also a Nobel Prize winner.
Yes, he is.
I'm told that's the last, that's all the time. Maybe one more question, quick.
In terms of planetary exploration, do you think it might be wise to consider a paradigm where you have more discovery class missions instead of larger curiosity type missions?
Absolutely. I think we are in that, in fact, we have to do that. And on the space side, on the astronomy side, I actually headed up a white paper saying we should have a much stronger comparable program, the Explorer program. And the decadal reviewers for planetary sciences have said, yes, we must do the same in planetary sciences because we can't afford these big missions. There will be a decade or so where we're building more of these smaller missions before we're able to go back, I hope, with cheaper, large missions.
I would take the time to thank our speakers. This was very interesting and dynamic. Followed by question and answer period. This is a good topic for people like you who are starting their careers in the space sciences and technologies. It's an exciting time, and the world is changing. There are tremendous opportunities, and like the previous speaker said, I wish I was in your shoes. Our first speaker is Judy Pfeiffer.
I guess it's on, is it? Are they going to turn down the lights for us a little bit? No? I think all of the speakers want the lights down slightly so you can see them. Yeah. Hi, I'm a member of what one of the previous speakers called the silent gen. That is, people over 70 who are barely involved, they think. But because I'm...
We're going to get right into the next panel now. Now, this panel is discussing the role astronomy should play in public outreach, and this includes the challenges and opportunities seen by the astronomy community today. For this panel, moderating, we have Hussein Jerda, and he is the head of Communications and Public Outreach at the Space Telescope Science Institute, and he will be moderating this panel. And then we have Dr. Judith Pfeiffer, who is a professor of astronomy at the University of Rochester, followed by Dr. Neil Brandt, who is a professor of astronomy and astrophysics at Penn State. And finally, we have Dr. Martin Elvis, who is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Now I'll hand it over to Mr. Jerda.
Welcome to this session. It's a very exciting session. We have three terrific speakers, and I will be moderating. And our format will be that we'll have about 10-15 minutes talk for each one of the moderators.
The dust lanes and the spiral arms. The visible shows mainly the older population of stars. The X-ray shows and the ultraviolet show quite young, hot young stars and hot gas. Okay, I have posed a number of questions for your generation. The first thing I want to do is congratulate you for early on assuming responsibility for the future of space astronomy. I was saying to one of the other panelists that when I was your age, it never occurred to me that I would be worrying about the future of space astronomy, and so I'm pretty impressed that all of you are here today doing just that. The questions I think you need to be considering for the future, and I'm assuming that most of your future will be tied up in astronomy anyway, science, the science side, with NASA or an equivalent agency, is the proper balance between the flagship science missions, the very expensive ones, versus the focused smaller missions. Then I wanted to say that it's terribly important that early technology development take place, and NASA or whoever is doing the funding has to, in fact, invest more in getting the technology right, and I'll explain some reasons why I think that is true. We have to, of course, talk about the role of private versus public funding for astronomy. this is an issue because while commercial applications play a big role in private funding, what role do they play in science funding, and what are the problems you have to be aware of when that happens? The oldest of the panelists, and I knew that two of the other panelists were planning on speaking of fairly specific topics, I decided to focus my remarks on a sort of broad brush approach to astronomy in the future. And the picture that we see up here, it's a little hard, unfortunately, to see, but it's a composite illustrating the different, with each color representing a different wavelength range of telescopes that are observing or have observed in the past. The X-ray and ultraviolet is the sort of purple-blue color, and the visible Hubble is a yellowish color, and the red is the infrared. They all represent, of course, different components of the galaxy that we're looking at, a spiral galaxy like our own. The infrared primarily outlines